Beautiful day. Man. Glorious. You should play soccer, bro. You should be. It's a year ago. It's a year ago. Yeah. Oh, such a beautiful day. Man. Craziness. You could be out there training. I don't know. Hey, buddy. Hey. Good stuff, boy. Good stuff, boy. Yeah. Oh, yeah. right, we are ready. Let me just move Alicia over. There we go. All right, we are ready. Welcome everyone, all four of you. Can anyone confirm that you can hear me and see the stream?
Hello.
Hello.
Okay, we got one.
Yeah, one. Better than nothing.
I don't know where the video is, though.
That you go to YouTube, Mathcast.
Oh.
So I'll give you a second to do that.
Hello?
Hello, welcome.
So do I press the X so that I'm muted?
If you have no background noise, but if we hear a lot of background noise from your microphone, then you can mute it when you're not saying anything, or you can go into
Okay.
your user settings and select push to talk.
Connected to iPhone.
So,
Connected.
but on the phone, push to talk is
Turn
a
on
little
light. Turn on
inconvenient.
iPhone 4.
Okay.
Mavericks. Jasmine's
I'll try that.
Cassie's iPhone. Mobile
So
device
feel
not
free
found.
feel free to experiment and see what works for you. We'll just let everyone sort of trickle
iPhone
in.
disconnected. Ready to pair.
Hello?
Hello, you are extremely loud. So if you are watching the stream and want to chat, which is ideal, you need to mute the YouTube video. Otherwise, you're going to hear the same thing twice with a 2-second delay, which is going to be
Battery
really
5.
strange.
Connected to.
I'll say it in chat as well that if you're chatting here, you have to mute the YouTube video. There will be sound come. Oh, hold on. There will be sound coming from the YouTube video itself because some people watch just that and don't want to say anything. But if you're interested to actually say and ask questions and converse, then you'll use Discord, which means you have to mute the YouTube audio
iPhone.
because you'll hear everything anyway.
Connected to
So
iPhone.
we'll slowly start to figure it out as we go, but see what works best for you. In my previous class, for example, no one wants to talk, just like the real class. They just watch the YouTube video, but depending on what you want to do, there are audio coming out of both, but they're delayed, so you can't listen to both at the same time.
Connected to iPhone.
Does anyone have any questions at this time before we get going?
No.
I think I figured it out.
Okay, good. Whoever said no, you are very loud.
Okay.
So you can go into your user settings and turn down your volume or something. See what
Is that
works.
better?
It is still extremely loud. You're just super excited. We understand.
I don't know how.
What device are you on?
A MacBook.
So the Discord window should look similar. Do you see your name at the bottom left
Mm.
with a little gear, user settings? We lost her. just check my audio for a second here.
Hello?
What's up?
Oh, not much. So is this the right place for this?
Yeah,
Yeah, you're good.
everyone is just very loud, so check your audio.
Very loud. Check your audio.
Very loud. Your audio. Very loud. Your audio.
Whoa. You have to.
Very loud. Your audio.
Again, you have to mute YouTube if you're using the Discord chat. All right, we'll see how we go. Uh, it's going to be a learning process on both ends to get the audio mix ideal.
I can't hear anything.
Can you not hear me?
Hello?
It's
Hello?
pretty quiet.
My voice?
Oh, okay. Okay, now I can hear you.
I can hear
It's
you.
pretty
So.
quiet.
My voice?
Oh,
That's
okay.
quieter.
Now I can hear you.
I can hear you. So.
I don't know what everyone else is
Oh,
saying.
is it quieter?
Hold on.
I don't know what everyone else.
Okay. This is a learning process. My only concern is my voice loud enough for everyone?
Yes.
Okay. That's the only priority. Any other background noise you can mute and unmute or adjust. Any other noise coming from other people, you can check your settings and turn down your volume as long as everyone can hear me. Yeah, as a starting point, I think everyone can mute themselves until you want to say something. And you can always use chat. We'll figure it out.
So how do we mute ourselves if we're using it on our phone?
Uh,
There'll be a little microphone thing that you can just click on.
yeah, you're looking for a little microphone symbol. Let me check where it is on the phone.
Okay, thank you. I found it.
All right.
How do I?
We are slowly but surely starting our next chapter, which is going to be on trigonometry. Now, we're only looking for a very basic introduction here. So, for those that love trigonometry, I'm sorry, but we're not going to go into too much detail. And for those that do not like trigonometry, we won't go into too much detail, so it's not going to be too bad. So, let's just get a page ready here. Need to zoom. Okay, so trigonometry, it's all about angles. Now, we have a fairly good understanding of angles already in terms of how many degrees, what an angle size is. So if we make a random little angle, like that, and then we have a little arc coming from a circle that I'm trying to simulate here, measuring or spanning this angle. We'll call this angle theta, the Greek letter. So, for example, this angle can be measured in degrees. So we have the degree measure of an angle. For example, this one, maybe 30 degrees. I was just guessing. So we grow up with degrees and angles, and the idea isn't too bad. If you say, "Oh, I have a 60-degree angle or a 90-degree angle," we have a good idea of how wide this arc is. So if we take a specific angle, and this was going to be our first experiment over here. We take a circle and pick an angle you want. That angle then has with it, well, that arc, that wedge, has with it a radius coming from the circle, as well as an arc that it spans. Now, the circle, the degree measure comes from breaking up the circle into 360 little wedges like this, filling the whole circle. So a single degree is a small little wedge, so that 360 of them will fit, will fill the circle. But if you take any angle, then you have a corresponding radius and arc length. If we fix the angle and make a couple of circles different size and a couple of wedges that correspond to those circles, let me try and do that. Circle time. Maybe like that. Let's see how this. No. Horrible. I'm just going to do 2 so it doesn't look disastrous. If we now pick the same angle, let's suppose we have a little 30-degree angle here, or something like that. I have this wedge over here, and I'll call the radius of the smaller circle R1, and its arc that it spans S1. And I have the bigger wedge as well for the bigger circle. Though the angle is the same, I have the longer radius R2 for the bigger circle, and of course a bigger arc SQ. And you can make many of these, but they all correspond to the same angle. The angle is the same. And if I make the wedge bigger, the radius and the arc length increase together in some way. If we measure these, we find that always for a specific angle, let's call it theta, good to give it a name, the ratio of arc length over radius is always the same. Oh, that was an S. Always the same. What does that mean? That means that the way that the arc length and the radius changes, the way it changes is connected to the angle. Now the problem is that I'll say it up. I'll say it up here. There is a flaw in. That was a W. There is a flaw in the degree measure, unfortunately. It's not a flaw that's immediately apparent until you have to do calculations and things. Just like percentages, if I recall percentages. Percentages are used to present information. This is an ugly E. I cannot live with that E. S. But when I use a calculation, I'm going to use the decimal version to calculate stuff. I only do percentages. I talk about maybe a 70% chance of something happening, but whenever I do calculations, I don't use 70%, I use zero point 0.7. They're the same concept, but different versions of the number. When we work in degrees, even though the degree concept seems simple in its presentation, and it is, it turns out that it's not very useful when I'm performing calculations and mixing degrees with other numbers, because the degree measure is a unit. And if I want to mix that with numbers of another unit, like maybe a length unit or something, I can't mix units. I can't mix units. I need to somehow make them the same. In fancier calculations, I could mix a degree quantity from an angle with a length measurement, and those can't just be added. I can't say 30 degrees plus 5 kilometers equals 35. That 35 is meaningless. So the issue is we can present and talk in degrees if we sort of just talk about a single angle, a single result. But when we perform calculations that mix quantities and units, then these numbers can't have units anymore. So because the degree is really a unit of an angle, because someone long ago decided to break the circle up into 360 pieces, that was arbitrary. We can't. The 30 is connected to what that degree means. We need to somehow get rid of this and see an angle in a way that's not connected to some arbitrary measure, but rather connected to lengths, like this radius and the arc length. So this is where this observation of these wedges come in. It will seem a little unnecessary, but whenever I have any calculation, it is really the cornerstone of any kind of success. So whenever we have a specific angle, instead of measuring it in degrees, we can measure it by taking the ratio of the arc length over the radius, because those two will always be sort of in check with each other as the arc increases, but the angle stays the same. So we can write theta is always arc length over radius. Now, that's not really immediately obvious how that's going to be useful, but we'll call this the radian measure of an angle. And notice how we don't have units anymore. This is a unitless measure. So it's just a number with no units attached, because whatever length measurement I used for the arc length, whatever length measurement I used for the radius, because it's at the top and the bottom, they cancel each other, and I have no units here. Which means I can use this freely, this kind of measure of the angle, I can use it freely in calculations and mix it with other numbers in any way, use freely in calculations. Okay, now what is this number? If I have a 30-degree angle, 30-degree angle, what is its radian measure? Okay. Well, let me just back up on that, since I don't want that to be in the middle of everything. So if this ratio works for... Oh, my polar bear froze. Aw, poor little guy. That's okay. I'm going to leave him for now. If this ratio of an arc works for any angle, as long as I keep the angle the same, this is also going to work for a full circle. For a full circle. So if I draw another circle, and say my arc, if you can call it that, my little wedge, is just going all the way around. I know in degrees, I am working with a 360-degree angle. So if I imagine this wedge here at the top, not really looking very wedge-like, because I went all the way around, I can still see it in the same way. I have a full 360-degree angle. What does that mean in this new radian measure? So now I'm going to call the arc length, because it's not really the same looking wedge. I'm going to call it the circumference, of course, for the circle. Circumference. And we're going to call it C. I still have my radius. So that means that my 360-degree angle is going to correspond to the circumference over the radius. And if I'm able to measure the circumference of a circle, which is tricky because it's a nice curvy shape line, and I measure the radius, that ratio, that fraction will be the radian unitless version of the angle that I can use in calculations. Okay, so let's put a pin in that for a second. Now, the Greeks realized this, and they investigated many circles. Let's draw some circles. Big circles, small circles, any kind of circle. What they did was they looked at they measured the outside, the circumference of the circle, and then measured the diameter for many different circles. So it's not the radius, but it's double the radius. The diameter is 2 times the radius. Even for this teeny tiny circle, did that as well. Many, many circles. They looked at the circumference and how the circumference compares with the diameter. And they found that the ratio of the circumference to the diameter is always the same. Now it was so unexpected to them that why any circle, and it's a basic shape, regardless of how big or how small the circle is, if you take the circumference and divide it by the diameter, it is always exactly the same. They called this ratio pi. And we now have heard of pi before, perhaps. We have an idea of it. But to them, this was absolutely revolutionary, that a basic shape like a circle can have this consistency hidden behind its properties. Whether you talk about the diameter or the radius, it's still the same key property of the circle, and its circumference is the other property. So we now know this, and they were then spending many, many years and lifetimes to try and figure out more about this constant pi. Now we know today it's 3.14159 and so on. That it never ends. It is a non-terminating, non-repeating decimal number. And the fact that this fairly complicated kind of number that it never ends and it never repeats itself occurs in such a basic geometric shape. The more you think about it, the more strange it actually is. Anyway,
Well,
so
can I ask a question?
yeah, absolutely.
I'm just trying to figure out, how do you measure circumference? Is that just going by the angles, like the
No,
of?
it is tricky to do it accurately. What we sort of a basic elementary school way of doing it is to take a piece of string and try to be accurate in laying it around the circle, then take the string and stretch it out and measure it. But the question of of accurately measuring something like the circumference of a circle is not, it's not the easiest thing to do. So you can
So
easily just approximate uh, this ratio. But if your approximation is accurate enough, you still see that the ratio is pretty much always the same.
so are you recommending we have a bit of string on hand if we have a test involving this?
No, well, this is what we would have done in class if a certain virus didn't spoil it. But so we would have had string to try and measure the circumference of a circle because that's sort of an elementary school first attempt. Now, in truth, what they did, what the Greeks did, is put where can I draw this? If I take this circle, if I take this circle on the right here, what you could do is put a polygon inside it, like we know how to do. Hint, hint, cough, cough. And you can calculate the perimeter of the pentagon very easily because they're straight lines, so you can easily measure them. And then you can, with similar methods, put the same size polygon, pentagon, you can put it around so it touches, so the circle touches the edges. Now this is a very rough sketch, of course. It's not going to look that great, but you get the idea. And then measure the perimeter of that pentagon. And the more sides you use for your polygon to put inside and outside the circle, the smaller these gaps are going to be. This is sort of your error gaps. So the higher the side count of the polygon inside and outside the circle, the smaller these gaps are, and the closer those perimeters are going to come to each other. And they're going to squeeze the circumference of the circle between the two of them. So by decreasing the gap between the perimeters of the polygons, you are getting a better and better approximation of the circle circumference. And then if you look at the pattern, so you're looking at the, let's write it as perimeter of n-gon inside is going to be less than the circumference of the circle, which is going to be less than the perimeter of the n-gon outside. That's always going to be a little bigger. So with this always being true, if you just then increase n, the size of your, let's say the size of your polygon, then it squeezes the circumference between the two. And those two are always easy to calculate. There are formulas for the left and the right of this inequality chain. And you can then squeeze the C value to how accurate you want it to be. Now, of course, there's some math and some exploiting of the pattern. How do we notice a pattern when we increase n and so on? But it can be done, and you can very accurately measure the circumference by way of polygons instead of string. But of course, that's not elementary school level, so the string is a good starting point to give you an idea of the circumference and getting this ratio. That was a very
All
long
right,
answer. I'm sorry.
so this thing you just showed us, this is just an advanced way of doing it.
Yeah, so I mean, the Greeks wouldn't have used the string for very long before realizing that this is not going to get us our accuracy that we want. But they did
Okay.
understand polygons and they had formulas for everything about the polygons, so they could use that to approximate the circumference of a circle very accurately. So measuring C accurately is not ultimately a very big challenge. Well, it wasn't for them. All right. I was just answering Steve. It's a good question. I mean, uh, how does it actually work versus how do I present it at elementary school? It's a good question. So I can very easily introduce the concept of pi at an elementary school level. I'm just not going to get a lot of these decimals. I'm not going to get, maybe I'll get to point 1, but my string measuring approach isn't going to be very accurate to get the 4, the 1, the 5, the 9, and so on. And the Greeks had the um, challenge they set for themselves to get as many digits of pi as they possibly could. And for that, you need to be extremely accurate. So back to this pi being the key to figuring out how we can represent angles in something that is a little more calculation friendly than degrees. And of course, all of this is in the book. You technically don't have to write down anything. So let's get some space here. Oh, I didn't want to do that. Let's get some space. We're running out of space. Okay, let's get back on track. So pi is a constant, and it's always, for any circle, the ratio of the circumference of the circle over its diameter, which I can write as the circumference over 2 times the radius. Okay? Now, that means that if I just want to get rid of this 2, not loving the 2, if I multiply both sides by 2, that'll get rid of my 2, and the circumference over the radius is equal to 2 times pi. So they just happened to measure the diameter. You could have very easily measured the radius, and then you get the constant, which is 2 times that 3.14. But now that means if we look back, circumference over radius, circumference over radius is what corresponds to 360 degrees. That means that 360 degrees correspond to 2 pi. Or, the way I like to remember it, 180 degrees corresponds to pi. And this is going to be the key to convert between the degree unit, which is definitely how I am introduced to angles, and how I present angles in an answer or in a question. But whenever I use a calculation or have the need for a more complicated calculation, where more than just a single angle is involved, this radian measure is the alternative way to refer to the exact same angle. So we just have to remember that these are units. We think of, so here our unit name is a little circle. Here, I know the radians is unitless, but in order for me to keep track of whether I'm in this radians situation, we will name it as RAD for radians, just to indicate that I'm not in degrees, I am in this unitless method, because there are others as well. So the only thing I have to remember, my reference pair, if you will, I have a crazy cat running around. What is happening? Anyway, my reference pair, just like I said, like 2.5 centimeters correspond to 1 inch, 1 inch, just like that, or 2.54, if you want to be super accurate, which I don't. We now have a reference pair for angle measurements, and the only one we need. We had a lot of length measurement reference pairs and conversion pairs for angles. We just have this one. But that means that I am going to approach the unit conversion in the same way as I would length conversions. So let's make a new page. Let's make a new page and see our first exercise in this chapter and in this new format. It's exciting. Are there any questions so far? So you can look in the book. We would have filled in the exercise 15.1, measured the arc with string and the radius, and found that the ratio is the one that stays consistent, constant pi. We would have done the circle, and we get that the ratio of circumference over diameter is this pi. We would have gotten fewer digits, but still. And then we have proposition saying, reminding us that pi is equivalent to 180 degrees. So now we're in exercise 15.3. Let me just pause to check. Is everyone still with me? Any questions? If you are worried about your volume or your background noise, for a simple yes, no, you can use the chat or whatever you want. I do not check the YouTube chat, just so you know. I see there are some chats. I do not check them. It's covered by my Discord window, so I will not respond to that very often. So if someone sees there's an important chat in YouTube, just let me know in Discord, because that's the one I'm keeping an eye on. Let me just go through the YouTube chat here. Steve was a good volume when he spoke, but there was no need to mute. Steve was good. You can always adjust your personal mic settings when you go to user settings. Mine, everything is maxed, but I'll double check in a second here. Let me just check if my sound, I can't even check my microphone sound. Oh, that's true. Maybe I don't even notice him being loud anymore. Yeah, I have all the volumes. Mine is maxed, so. But you can very easily turn yours down if it's too loud.
Yes, Steven, I think people are complaining about the YouTube being a little bit quieter than the Discord stream. I know I think we're all.
Now yours is extremely soft. I can't quite hear you. Hold on. Let me turn up my volume. Okay, say again.
I think people are complaining about like the YouTube volume being too low, like on your end, like from you.
Okay, let me go double check. I can turn my mic volume up. When I tested it, it went into the red, which is bad. That may be better. This one's maxed. Everything is maxed now.
Right on. Okay, I'll turn my mic up. I just turned it down.
What you have right now is See, because I can adjust my output volume as well. That's all good. I don't know. We'll figure it out. As long as the background noise is minimized, I think that's the most important thing. Listen through Discord and there's no echo and mute YouTube. Yep, that's what I would do. But it's hard for me to know because everyone's device is different, everyone's settings are different, everyone's headphone, microphone's different. I really can't make general recommendations on the receiving end. All right, so how do we convert between degrees and radians? Where's my mouse? There's my mouse. Let's see if this is still. Did everything freeze, or we are good to go? Everything seems quite frozen on the YouTube end. Open a new window and see. It's more delayed for me to check my preview. That's why I can't tell. Okay, I think it's okay. Exercise 15.3 you see in front of you as well, because you have the book. We want to convert 60 degrees to our radian measure. So it's really exactly the same as the length measurement conversion, the length unit conversion. I just have to remember that this little circle is the name for that unit. So 60 degrees times the reference pair. I'm going to have degrees at the bottom and radians at the top. Then the little degree unit will cancel, so to speak, and I'll have my radians at the bottom. Now you can look at the calculator, has pi as a button. You don't have to approximate pi, so you can calculate it. I have a calculator quickly downloaded here. Let's see, is pi visible over here? There's pi over there. Don't get intimidated. Whoa, that was loud. That was me. Sorry. Don't get intimidated by all the extra buttons.
Well, doesn't it say not to use a calculator without using one?
I just want to show you both. If you want to use the calculator to see what that number actually is, you can do it right now and say 60 times pi divided by 180, just like we would for the other measurements. 1.047. That would be radians. But what we end up doing with these familiar angles, like 60 degrees, 30 degrees, and so on, is we just take the 60, and then we have the pi, and in the bottom we have 180, and we simplify that as much as we can. Well, 60 goes into 183 times to get pi over 3 radians. So it's a little bit cleaner to have it in fraction form than in a decimal form where we have to round. If I now have to use this further, the pi over 3 is not rounded and it's perfectly accurate because pi is built in to my calculator with as many digits as I can possibly need. Whereas if I round it early and then use that in a future calculation, then I might lose some accuracy. So there's no need to worry about the calculator really ever. Pi over 3 is a very nice and clean version. What else do we have? 30 degrees. So 30 degrees times my reference pair, which is always the same. I just have to put the degrees in the bottom. So 180 degrees corresponding to pi You don't have to write radians, but just to show that this is the other quote-unquote unit is then going to be in the correct units because the degrees are canceling. 30 over 180 is going to be 1 over 6. So I have pi over 6 radians. So people get a little, I guess, intimidated or flustered or something with this new radian measure. But if we keep in mind that we are not changing the angle, we are just giving it a different name. It's still the exact same angle. This name just turns out to be more safe in any sort of calculation, regardless of how complex. Now, we don't necessarily see that complexity, admittedly. So even after our discussion, you might still feel like, what's the point of radians? I don't see the point. It's because we stop before things get complicated. If you do anything that's even a little bit further than we are, there is no choice. Degrees are only existing because we grew up with them. There's a tradition of degrees, but they're not useful in any sort of calculation. The other one is pi over 4 2 degrees. So if I have pi over 4, that means I'm in radians. If they say nothing. I need my reference pair, which now will have radians at the bottom and degrees at the top. So then if I simplify the radian cancel, they cancel each other. The pi cancels this pi. 180 over 4 should be 45 degrees. So after a while, we get used to the familiar angles. 30 degrees, 60 degrees, 45 degrees, 90 degrees, and so on. And we're not anything more complicated or weird. You can always use your calculator. Number 4, 5 pi over 4 degrees. 5 pi over 4, that would be in radians. I just have to, I always have the same reference pair. There's nothing to do. I just have to figure out which way to put it. And the bottom one is whatever the current units are. That way they cancel. The pi cancel. This pi. 5 over 4. 180 degrees. Now you can do that on your calculator if you want to. Certainly not an exercise in fractions. So let me just demonstrate. That's okay as well. 5 times 180 divided by 4 equals 225. Whoops, that was a line. 225 degrees. I think we have one more. 270 degrees to radians. 270 degrees. Are my examples are in the book. I'm on page 107. In chapter 15. I'm getting my examples on page 107 in chapter 15. I'm pretty sure this is the book that you have. Okay, good. 270 degrees. So now I'm in degrees. So I need to, for my reference pair, put 180 degrees at the bottom, pi radians at the top. It's really quite simple. Because it's always the same reference pair. You don't even have the length unit conversion issues of figuring out the shortest path and making the chain. There's no chain. That's it. So 270 over 180 It's nice to have this in a fraction form. Now your calculator does have that ABC fraction button. I don't know if mine does. Somehow I think not. I don't immediately see it. No. You can just type that 270, the ABC button, and then 180, and then equal, and it should give you 3 pi over 2 or 3 over 2, and then I include the pi. So your calculator is a little better than mine. I just quickly got one to cover all the basics. All right, so converting between the different ways of representing an angle is easier than unit conversion we've seen before because it's only one reference pair.
Um,
Any questions? Yes.
yeah, you completely lost me on that last one. So I'm not entirely sure, like this 270 and A, B over C. Like
On your calculator, there's an ABC button. That's when you want to calculate in fractions. The physical sharp calculator that you should have in front of you. Otherwise, you could just ignore that. We can also just simplify 270 over 180. I was just speeding up because I see it's 1020. We have a new plan. If you looked at the announcements, that we have one streaming lecture, 9:30 to 10:20ish, and then our second hour is just open for questions of any kind, like office hours would be. So in a second, I'll reset the stream, and we can continue with any questions you may have. We still have a second hour. It's just not a duplicate lecture anymore. So if we simplify 270, now we have to go to fractions. See, no one likes this, but it is a skill we may need to have. We can find a common factor, divide by 3 on both sides to get 27 divided by 3 is 9. 18 divided by 3 is 6. And then you can do it again. 3 divided by 3 to get 3 over 2. The calculator can just do that for you. And then I just include the pi because pi is a weird number and it's not going to mix with these nice integers. Yeah, so if you use the ABC button, that's how you input fractions. I think if you look at the second function above that, it's a C over D, maybe. I'm totally guessing. I don't have the calculator with me. And that is if you want to keep them improper fractions. So you have your answer, and then you press second function, that ABC button, and it'll make it 3 over 2. 1.5 is equal to 3 over 2. So whichever version, the mixed number version, we don't use in any way that is not extremely basic in elementary school. Improper fractions are just safer. Otherwise, the whole number portion and the fraction portion get detached from each other, and it just creates confusion. What is happening around me? Anyway. Any questions for this class before we switch to the office hours portion, which you are welcome to stay for and use asking questions on this or asking any other questions, open discussion, exactly the same classroom chat, everything's the same. I'm not duplicating the lecture. It's just a session for anyone who has any questions, like office hours would be. Except you don't come to my office. You just come to the Discord class. So if you have questions you don't want anyone else to see or hear, we have the private rooms for that. But we'll start in the main classroom to see if there are any questions on this first part of the trigonometry section. Is there anything we want to see? Is there anything we want to see on the notes that I wrote? Because I'm going to end this stream and then restart the office hour one. Problems? So we have more to do, of course. That's only a part of the chapter. You can look at problems 15.1 and 15.2, which is the conversion the conversion question. So we have to convert from degrees to radians, and we have to be able to convert from radians to degrees. And so far, that is all we have done. We will do the second half tomorrow and see how far we get. Any other questions for the lecture portion? If anyone's not sure what's happening next, just stay. We'll sort it out. This is new to many of us, so it might take a while to get into the swing of things. But I think we're simulating our in-person class as closely as we possibly can. So I will finish the stream here, but I will continue, start another one. And I'm still in Discord.